Hello guys, Mr. G here, and we are going to be doing another video for the grade 11 related to vectors. This time is going to be the last video on questions. Next time, if possible, we're going to be doing an experiment, I promise already, and we're going to do some questions now. As you can see here, last time we worked with two different questions related to vectors, in which the second one was a little bit tricky. So let's going to do another 3 questions today. They are not going to be that difficult, and we'll take it from there. So the first question we're going to be solving, say the figure shows two forces F1 and F2 of equal magnitude which act on an object, and you have the two forces there. 3.1, calculate the resultant of the horizontal components of the two forces there. So saying that, we're looking for the horizontal component. Please note that each of these forces have a horizontal component which we can call F. In this case will be F1 in X, and we also have a vertical component which in this case will be this arrow here, and it will be F1 in Y. According to the angle we have here, in this case is this angle here, F1 in X will be equal to the product of F1 multiplied by the cosine theta. Why cosine theta? Because this is adjacent side to the angle, and F1 in Y will be equal to F1 sine theta. Why sine theta? Because F1, this one here that we can see there, this vector here is equivalent that if we draw a line here, these two are the same, F1 in Y, and you can see it's the opposite side. When you go to F2 also have a horizontal component here in the x-axis, which is going to be F2 in X, and we repeat the same thing because this one is the angle we are looking at, this one is the adjacent side, and is therefore the product of the hypotenuse, which is F2 multiplied by the cosine of theta, which in this case is 35 degrees. And here this one will also have a vertical component which you can see there. This is F2 in Y, and this will be equal to F2 multiplied by sin theta. You can see that that one will be the opposite side. This one here, as we can see, this line here is the same as this line there. Okay, so this is another question. The question asks you to calculate the component, the two resultant. Okay, but to do that one, we first have to calculate each of the horizontal component, and we are going to do it in the same place here. I don't think it's a need for us to do it down, so we are going to calculate it here. If 1 in X is equal to 100, cosine theta is cos 20 degree, and F1 in X will be equal to 93.97 Newton. And if we go to the second force, when you substitute, is F2 in X equal to 100, because each of them is 100, cosine 35. The answer here is going to be 81.92 Newton to the right, or to the positive x-axis. So this is what we have, but we are looking for the resultant in the x, or horizontal component. So the resultant here must be the vector addition of these two vectors. Note, one is pointing to the left or to the negative x-axis, and one is pointing to the positive. This is to positive x-axis there, and the other one, this one is to negative x-axis, or in the negative x-axis or left. It does not really matter the way of you giving directions here, guys. Now for question 3.1, all we have to do is to add those two components, the vector addition of F1 in X and F2 in X. So that's all we are going to do here. But before doing that, we have to select a direction as positive, and we want to say left is positive. It means everything in the other direction is a negative. Okay, so we have here, and if we do the axis, then we can say it is negative. We're going to say that F net in x, because that one is the one we are calculating, is equal to f1 in x plus f2 in x. All right, now what forces we have here? F net in x is equal to, then f1 in x is 93.97 minus, this one is going to be negative, 81.92 newtons. And when you calculate that one here, guys, you will get 12.05 newton left, or to the negative x-axis, because it's going to be pointing to the left, or negative x-axis. So those are the two options there, guys. Okay, now question 3.2 is asking you to calculate the resultant of the vertical component, and to do that, first we have to calculate each of the vertical component, but I think now is already understand, so I just going to substitute and calculate for you. Then once you have this, note that both of them are pointing up, so we have to add the two components. So question 3.2, we have that f net in y is equal to f1 in y plus f2 in y, and we just have to substitute here, guys. This is 34, sorry, that is a 4 there, 34.2 plus 57.36, and the answer here is 91.56 newton up, or to the positive y-axis. You can just say that as well. So this one is quite easy, guys. We have here the answer for the component in x, and here we have the answer for the net resultant force in the y-axis. And now the final question say calculate the magnitude of the resultant of vectors f1 and f2. In other words, they want the final resultant. So 3.3, we have to use Pythagoras. F net is equal to the square root of f net in x square plus f net in y also square. This is simple Pythagoras, okay? So we done it before. All we have to do is to substitute the values, the square root of 12.05 square plus 91.56 square. Okay, and the final answer is 92.35 newton. Note the following here about this answer. The question say calculate the magnitude, and therefore we do not have to give a direction. So this is all about question 3. Let's go to see question 4. Now question 4. Say tugboats are used to move ships in a harbor. The diagram below shows a tugboat P pulling a ship with a force of 7,000 newton. So here FP, I'm going to write FP here, is going to be equal to 7,000 newton. Alright, and you have here that FQ, and they are telling you FQ there is equivalent to 4,000 newton. They are giving you that one in the equation to the left. So one is to the right and one is to the left. Determine the net force exerted on the ship. To do this question, the first thing you must do is to select the direction. And this is very important. So we are going to write that direction there positive, which is right. So right is going to be positive for us. Therefore, FP is positive and FQ is going to be negative. So let's answer that question 4.1 real fast. Question 4.1. Now they're asking you to calculate the net resultant force. So F net here, no Pythagoras because they are along the line, is equal to F1 plus F2. This is a vector addition. When you substitute, you have that is a 7,000 positive because it's to the right, plus a minus 4,000 negative because it is to the left. You don't have to write the plus minus. You can still write 7,000 minus 4,000, and that gives you 3,000 Newton. Now, the question said here, determine the net force. Net force have direction, so the answer here is positive. As you can see, it's a positive answer, and we said that positive is to the right. It means that the final answer we're going to give the direction, and it's going to be then 3,000 Newton to the right. That is the very final answer of this specific question. I hope you understand. It's quite simple. Question 4.2 say the tugboat now changed the applied force on the ship. So now we have a new situation here. They change direction and they say change magnitude. Determine by means of accurate scale drawing the magnitude of the resultant force. Use the scale of 10 millimeter represents 1,000 Newton. Note the following: 10 millimeters is equivalent to 1 centimeters. So that is important. And then if you convert then 6,000 Newton, it will be equivalent to 6 centimeters. Alright? 6 centimeters. And 8,000 Newton will be equivalent to 8 centimeters. So you are going to draw those vectors there. Now, the best option is to use tail to tail, but you can use either tail to tail or tail to head. This is 4.2.1, if I'm not mistaken. I want to respect the question. Yes. So now, with your ruler, not with calculation, with your ruler, you are going to make sure you measure 8 centimeters up, straight up. For example, this one with the ruler, guys, this one is the 8,000 Newton, you see there, which would be equivalent to 8 centimeters. But you are not going to write, or you don't have to write the 8 centimeters, you write the 8,000 Newtons. You can see it here in the drawing, guys. It's not different, it's not difficult. Now, you have to draw 6 centimeters to the right. And here we are. This one is 6,000 Newton and it was 6 centimeters to the right. It's very, very simple. Now, where is going to be the resultant? So if you think you are going to struggle doing it tail to tail, guys, then you can come here and do it using tail to head. So you take this vector as it is and you are going to place it on the head of the first vector. As you can see there, I left the head behind. Please note you cannot leave the head behind, and be careful with the head, don't make the vector bigger. So all this move there, and this one is the 8,000 to the north or up. Okay, now where is the resultant? The resultant is the vector that is going from the tail of the first vector to the head of the last one. And this vector here is vector R or FR. It does not really matter the heading. However, let's write FR. This is the resultant vector. The other option is to draw the parallel to each one and is the diagonal from the both tails to the head of the where the lines cut. Now note the following: the magnitude of this one must be measured with the ruler, and when you do that, if you do it accurately, you will get 10 centimeters, and 10 centimeters, my lovely children, will be equivalent to 10,000 Newton, and this one is the magnitude of the resultant force. Note the following: this question said the magnitude of the resultant force, so we don't have to give direction. However, if they ask you to give a direction as well, all you're going to do is to measure this angle here using a protractor, and that one will be the angle there. If you want, you can do it to practice there. If you measure this one with a protractor, you should get that is 53,1 degree or 53,2 degrees. That will be the direction if they ask you, but in this case didn't ask you. Note, this must be accurate done with a ruler, no with calculation. Okay, so we are done with that question. Now the question 4.2.2 say calculate the direction of the resultant force with respect of FP. Now important, if we go to this drawing with respect to FP, in other words, if we move this one back, If we go back to the tail-to-tail method, this one, guys, is the tail-to-tail method. Remember I said if you do that one, you need to have the diagonal line to each side there and there, and you can see that the resultant is exactly the same. It's just where the diagonals of where these parallel lines cut each other, there we go, but the result will be exactly the same. You can see the drawing. Let me try to move this one quickly. There it is, the one. Okay, now the question asks you to give the direction, say calculate the direction of the resultant force with respect to FP. Now with respect to FP, the angle they want you is this one here. This is the angle they want you to calculate because it's with respect to SP. That is the angle they want you to calculate, and they don't say measure, they say calculate. So how are we going to calculate that one? Remember, tan theta is equal to opposite side divided by adjacent side. The opposite to the angle is this side here. I hope you're looking what I'm marking here. This one is the opposite side, which is equivalent to the 6,000, and the adjacent side then is this 8,000 there. So tan theta will be equal to opposite, which is 6,000 divided by 8,000. Okay, but you have to get theta. So theta will be equal to 10 to the minus 1 of 6,000 divided by 8,000. And when you calculate that one, guys, it's going to be equal to, then you will get for the answer 36,9. 36,9 degree. That is the angle they want you to calculate, it say with respect to FP. And then we're going to do the last question. Another ship is pulled by a tugboat R, which applies a force of 5,000 Newton at an angle of 30 degrees with respect to the horizontal on the ship, as shown in the diagram below. Calculate the magnitude of the vertical component. They only want us to calculate the vertical component, and the vertical component will be this force here. Vertical, this is the force in the y-axis. How do you calculate that one? That one is opposite to the 30 degree. So if you do it, which I am going to do it here, you have that is opposite side, okay, and this one is the hypotenuse. So F in y is going to be equal to F multiplied by sin theta, which is equal to 8,000 multiplied by sin 30 degree, and the final answer is going to be 4,000 Newton. And that is the final answer, guys. That is the final answer here for this specific question. And that is the end of this question. That is the end of this question. It's quite simple. It's not that bad. It is more intimidating than actually what it asks. So let's go to the next one, and the next one could be tricky. It's the last question we're going to be doing in this video. So now we can go to question 5 when we finish with question 4. An object A of weight W is supported by two cables attached to the ceiling and wall as shown. The tension in the two cables are T1 and T2 respectively. Tension T1 if 1,500 Newton. And guys, the last question of the previous video was just a question very much the same like this one. Draw a vector triangle to show all the forces. Now, a vector triangle, they do not want the vector diagram, they want a vector triangle. And let's do quickly that one, 5.1. Now, this is at equilibrium, so the vector triangle is going to be a closed, it must be a closed triangle. They don't say do it at scale. So all we have to do is the following here. We have first to draw vector T1, and note I am not working at scale. They don't say do it at scale, they say draw a vector triangle, so I'm not going to struggle doing it at scale. So that is T1. As you can see, I move it from here, I move it to this side. So I am going to draw now T2, which is pointing in the other direction there, and here would be T2. Once more please, I'm not working accurately at scale. And now the last one is the weight, which is pointing down. That is W, and as you can see, it is a closed triangle because the system is at equilibrium. Now calculate the tension T2. Now if we go here, now we're going to do a small analysis here in this drawing quickly, and we did it before. They want us to calculate T2. Now what we have, let's first of all draw the axis real fast here. And here we have the axis. This one here is the x-axis and this one here is the y-axis. Now we have F1 and we have, T1 and T2. This is the symbols they're using. So let's draw those vectors real quickly now in a vector diagram. So for example, here we are going to have T1. All right, this here is T1. Okay, and on the other side you have T2. On this side we have T2, and therefore let's draw, or let's represent here T2. This one is T2 and you can see it here. T2. What else we have? We have the weight. The weight is pointing straight downwards here. So this red one represents the weight. Okay, so now let's look at the angles quickly, guys. The angle may be tricky, but it's given to you there. And this is alternated between parallel. So this angle here is the same as this angle here. And this angle is going to be 40 degrees. And this angle here that you can see will be equal to this one here because they are alternated between parallel. So that is important. It is given to you guys. It is given to you. So let's take all this drawing down there because I'm not going to get confused with everything I have here. And this is what we actually have. Okay, now saying that, let's quickly have a small analysis and you will see this work is been done before. This T1, it is not in the axis and therefore we have to get a component. As easy as that, nothing to say. It must come here and you will have here in the X, you will have T1 in X, which according to the angle you have is the adjacent side and therefore is equal to T1 multiplied by cosine of 40 degrees. This one is given by math, it's not even physics, okay? And now here on the other side, this one must also come to the x-axis and we have here the component. This one is T2 in X. And note the following, that one is the same as this side here, so it becomes the opposite of the angle, guys. It's simple math. It's the opposite side to that 60 degree. If you want to calculate the other angle, you're welcome to do that. So T2 in X is equal to T2, but because it is the opposite, it's not going to be cos, it's going to be sin theta. Okay, and guys, we are almost done with the question. Note the following, because the system is at equilibrium, it means that all this side here must be equal to all that side there. So we can say now that T1 in X is equal to T2 in X. Why can I say that? Because the system is at equilibrium. T1 in X, it is what? That is the formula right here top. So it is going to be T1 cos 40 degrees according to the formula there. Who is T2 in X? It is here, the blue one is T2 in X. It's going to be T2 sine theta, but it is 60 degrees. Okay, now we are looking according to the question. It asks us to calculate, here it is, calculate T2. We do have T1. So we substitute what is going to be T1. T1 is equal to 1,500. So T1 is 1,500 multiplied by cosine of 40 equal to T2 multiplied by sine 60 degrees, and we are done. This is just simple maths that you are going to calculate. And then T2 is equal to 1,326,83 Newton. We are done. This is also a question that could be tricky, but the only tricky thing is to notice that these are equal. this one here, because they are at equilibrium. And guys, with this we are done this question. Thank you for watching. I hope it helped. I'll see you next time with another video. Subscribe for the channel, thumb up. Thank you, Mr. G here.